Welcome back to the deep dive. Today, we're unpacking a chemical phenomenon that, on paper, it just seems to defy logic. We're talking about materials that perform one of chemistry's greatest tricks. They absorb mass hundreds or even thousands of times greater than their own.
It's an incredible thing to see.
It really is. You're looking at this microscopic dry pellet that, when you add water, expands into a fist-sized lump of gel, and it locks that water away permanently. So the core puzzle we're getting into today is, okay, let's unpack this. How do chemists actually engineer a material to achieve this kind of ridiculous expansion just by adding liquid?
What you're describing there is the functional elegance of superabsorbent polymers, right? SAPs, for sure.
Right, SAPs.
And this isn't just a very thirsty sponge. It's a meticulously engineered chemical, exploit. It's a polymer that's designed specifically for this massive retention capacity. It holds water so tightly you can squeeze it and nothing comes out.
Wow.
And our sources confirm that while, this technology is most often associated with consumer goods like baby diapers,
Yeah, that's what everyone thinks of.
that's their economic backbone for sure.
Yeah.
But they also have really serious high-stakes uses. For instance, the exact same chemistry is critical in some specialized equipment used by firefighters.
Okay, that immediately gives us our mission for this deep dive. We need to move past that classic diaper example and really understand the molecular architecture that allows for this. Then we need to quantify the true scale of their power because the numbers are just massive. And finally, trace their utility across these really different fields from, agriculture to high-risk industrial safety.
Right.
We're here to give you the shortcut to understanding this surprisingly versatile material. So let's start with the mechanism itself. If we want to understand how a tiny dry particle can physically blow up into a giant gel, we have to look at the ingredients. This is where it gets really interesting.
It is.
What are the building blocks at the molecular level that set this whole thing up?
It fundamentally relies on the structure of polymers. So these long repeating chains of molecules. Think of them as these vast interconnected strands. The core secret, though, lies in what's attached to these strands.
And what's that?
Specific chemical groups that carry a really high concentration of electrical charges. And importantly, these are typically negative charges.
So in their dry state, these negatively charged bits are all crammed together.
Exactly. They're forced to sit very close to each other, so they're constantly repelling, but the dry, tight structure of the polymer just holds them in check.
It's like a coiled spring almost.
That's a great way to put it. It's a bomb of potential energy just waiting for a trigger.
So the repulsion is already there, it's just contained. But when we introduce water, we're giving it a medium to, express itself.
Precisely. Water molecules are polar. They have a slight positive and negative end. This lets them efficiently hydrate those charged sites all along the polymer chain.
Okay.
So as water rushes in, it surrounds these negative charges, and it sort of shields them from the chains next to them. This allows that negative to negative repulsion to finally push the polymer chains apart with just tremendous force.
So the chains fly apart, creating this immense internal volume. But wait, if the chains are flying apart, why doesn't the polymer just dissolve? Like a grain of salt or sugar. What's holding it together?
That's the critical piece of the engineering. That's what makes it more than just soluble. The chains aren't just loose spaghetti. They're actually tied together at certain intervals.
Right, together how?
By chemical bridges. We call them crosslinks. And these crosslinks create a three-dimensional network, like a permanent net or a scaffold.
Ah, I see. So it can't just break apart.
It can't.
Yeah.
And the degree of this cross-linking is the key parameter that scientists use to control the swelling. If you have very few crosslinks, the polymer swells immensely, but it's weaker and it's slower.
And if you have more?
If the density is high, it swells less, but it's much stronger and absorbs way faster. So scientists literally tune this density to meet the needs of the application. It ensures the water is trapped physically inside that structure. No dissolution, no leakage.
That explanation gives such a clear picture of the architectural genius behind this. But now let's move beyond the how and quantify the power. We need to put the super in super-absorbent polymers.
The scale is really what makes this technology so disruptive. And when we say thousands of times its weight, we're not being hyperbolic.
Some of the numbers are hard to believe.
They are. While, common commercial polymers might absorb 300 times their mass, some high-end variants can absorb up to 3,000 times their weight in pure water.
3,000 times. Let's try to put that into context for you. Imagine a standard bag of granulated sugar, which weighs about 5 pounds.
Hmm.
If you had 5 pounds of the most efficient SAP, it could theoretically absorb 15,000 pounds of liquid.
Yeah.
That's like absorbing all the water in a small car, or a dozen bathtubs.
And that transformation from this small, hard granule to a stable, voluminous gel,
Mm-hmm.
it's just astonishing to watch.
But okay, there has to be a catch, right? A nuance.
There is. And it's a very important one from the sources that you need to understand. That 3000x figure that's typically only achieved with pure deionized water.
Ah.
SAPs are highly sensitive to the presence of ions and salts because the whole mechanism relies on electrical charge repulsion. Introducing other positive ions like sodium or calcium interferes with the system.
How does it interfere?
Well, these positive ions act like tiny chemical shields. They basically neutralize the repulsive negative charges.
So when they hit salt water, or critically complex bodily fluids that have salts and electrolytes, the absorption capacity just plummets. It's a chemical trade-off.
It absolutely is. In practical, real-world applications, like in hygiene products, that absorption capacity might drop from 3,000 times its weight all the way down to maybe 60 or 70 times its weight.
Which is still a lot, but it's not 3,000.
Not at all. And manufacturers spend enormous effort balancing that desire for maximum swell with the necessary function against the ionic content of whatever liquid they're targeting. This is why the material in a commercial diaper versus an agricultural soil additive can be so different. It's a highly targeted design process.
Understanding that scale and its ionic sensitivity moves us neatly into the practical uses. So what does this all mean when we talk about the real world?
Yeah.
Let's spend some time on this because the applications go so far beyond just consumer products.
Absolutely. The core utility is controlled liquid containment, and that solves problems in 3 very different arenas: resource management, hazard mitigation, and specialized engineering.
Okay, let's start with resource management, specifically agriculture and soil. This seems critical for a world that's increasingly dealing with drought.
It is. When you mix SAPs into the soil, they function as these little dynamic water banks. They don't just hold water, they dramatically improve what's called water use efficiency.
So they help the soil hold on to moisture longer.
For much longer. In regions with intermittent rainfall, adding even small amounts of this polymer can reduce irrigation needs by 30 to 50%.
Wow.
What's really fascinating is how the plant gets the water. Since it's held so tightly within the gel, the plant has to exert its own energy, its osmotic pressure, to draw the water out slowly.
So it's not just flooding the roots.
Not at all. It ensures the plant gets continuous moisture between watering cycles, which is just crucial for seedling survival in really arid zones. It's a controlled, slow-release delivery system.
It manages the risk of both drought and oversaturation.
Exactly. And while this tech is extremely beneficial, we do have to note a trade-off. Traditional SAPs are often not biodegradable. They just stay in the soil.
So there's an environmental consideration.
For sure. A lot of current research is focused on developing biopolymers from things like starches to maintain that function while making sure they eventually decompose.
Okay, so that's resource use. The transition to hazard mitigation seems dramatic, but it makes sense. The core function is still containment. Let's look at fire safety. How did this polymer actually help firefighters?
It serves 2 main functions there. First, in structural firefighting, when you mix it with water, the gel you get is way more effective at coating surfaces than just plain water.
Stickier.
Much stickier.
Mm-hmm.
This polymer-enhanced slurry adheres better to walls and structures, and it provides a thicker, longer-lasting thermal barrier. It just insulates materials from the heat.
And the second function?
The second, and maybe more crucial role, is in handling flammable liquid fires, Class B fires.
Right, like oil or gas.
Exactly. Traditional methods use foam or sand, but specialized polymers can be used to encapsulate or just quickly absorb volatile liquids like hydrocarbons. This absorption immediately suppresses the vapor release, which is often the source of the fire.
So it turns the liquid hazard into a manageable solid gel.
A manageable, inert solid gel. It's much safer for cleanup than letting a flammable liquid run off somewhere.
Which changes the physical state of the danger. That makes containment so much easier, and that speaks directly to its use in chemical spills, too.
Precisely. If a highly corrosive or toxic liquid spills in an industrial setting, time is everything. You can broadcast a polymer material over the liquid, and within seconds, it's locked into a stable gel.
Preventing it from getting into drains or the environment.
It's an immediate stopgap for liquid migration.
And finally, let's touch on one of the more unexpected engineering uses that was in the material, something that sounds like it came out of a specialty lab.
We're talking about highly specialized moisture management, inside infrastructure.
Such as?
For example, in the telecommunications industry, certain high-tech cables are wrapped with SAPs.
Really? Why?
If the outer casing of a fiber optic cable is breached and water gets in, the polymer immediately swells. It forms a watertight localized seal that stops water from migrating further down the entire length of the cable.
It's like a self-healing patch.
Self-sealing capability, yeah. And it's far more reliable and cost-effective than trying to pressurize or constantly monitor these massive cable systems.
So, just to recap, we have a single technology that is simultaneously protecting global crops, neutralizing industrial hazards, and ensuring the integrity of our communications infrastructure. It's just remarkable how diverse the impact of simple molecular repulsion can be. As we wrap up this deep dive, it is genuinely amazing how a simple material driven by the electrical need for negative charges to push away from each other transforms into such a critical component across so many industries. We started with the visual shock of a tiny pellet swelling 3,000 times its volume, and we've ended up realizing that this massive retention capacity is solving challenges related to climate, to safety, and to modern infrastructure.
It really reinforces the immense value of functional chemistry. The polymer's ability to selectively absorb and retain liquid, despite gravity or physical pressure, it's an exploit of the fundamental properties of water and charge.
Right.
And that deep understanding is what allows these polymers to be tuned for performance, whether they're fighting ions in baby fluids or fighting volatile chemical spills.
So let's leave you with this final thought to explore.
If this super-absorbent polymer technology is already optimized to manage everything from drought and fire to chemical transport and cable integrity, where, in your own field, or even your daily life, is liquid control the biggest, most intractable problem right now?
What previously unsolvable liquid challenge could this versatile material tackle next?